Hello everyone and welcome to my Akai AX60 restoration video. I'm quite excited about this one because I've never seen this synth before in my entire life. It seems to be so rare out here in Australia, and it looks like most of Europe as well. So I was quite excited when I picked this one up. It's extremely broken and it needs a good clean and all that kind of stuff. I'm hoping to do the full restoration, but we've got a lot of work to do on the repair before then. So for a start, I've only got one voice. I'm not sure which key it's assigned to now. Not that one. I've lost all my voices. It's on. I swear it's on. Alright, I don't have anything now. Eventually I'd like to get the LED sliders installed too. They would look really cool, I reckon, especially in red to match the LEDs that are already on there. And this is quite an aggressive sounding synth. So red LED sliders would look awesome. And that would solve the problem of losing the slider caps, which not many of them seem to have all their slider caps. Looking on eBay and all that kind of stuff, a lot of them have them missing. So besides the whole polish up thing and the new sliders and probably put in new tactile buttons, fix a lot of the keys. Oh, it's working now, yes! Oh, but it sounds really horrible. There's some keys that looks like they've been snapped off too. So I will need to replace some keys. First, I think I'm going to pull all the boards out and clean out all the dust and replace all the components that I think normally fail. And hopefully we'll find that a lot of the problems just magically get fixed just by replacing things like the multiplexes and the logic chips and all the stuff that usually fails. And then at that point, if there's any big problems left, we'll use the schematics and trace out what's going on. Alright, let's get these boards out. So I've already labelled each of the plugs. Okay, so the CPU board's pretty easy to pull out once you've undone the screws and the nuts on the back. But the voicing board, there's these little plastic pins in the connector, so you have to push them out from the inside. So the only difficult bit are the connectors on the back. Once they're done, it's pretty easy to pull out. And the power supply, which is pretty easy, it's just 2 screws at the back and 2 at the front. Okay, so the boards are out. I've got the CPU board, the voice board, and the power supply. The power supply, I've already recapped it, so I've replaced these larger capacitors, and I will test that more once it goes back in the instrument. But first I'm going to work on the voicing board. So we've got our 6 CEM3394s. They have all the VCOs, the VCFs and VCAs are all on the same chip, so each voice has one chip. And there's some supporting circuitry around it, and there's some switches here. These are 4066 quad switches, the bidirectional switches. There's 4 in the one chip, and there's a row of chips down here which are 4051. They're multiplexers, so they're an 8-way, like an 8-way switch. There's some transconductance amplifiers and a whole lot of op amps in the single package too. So this synth has so many problems that we really can't start tracing it out on the schematic. So the best thing to do is to target the chips that are known to fail. And by far the worst ones on this board are these 3 4066 switches. So they are notorious for failing, and also these multiplexers can go. So I'll replace them too. after that I'll probably test and see how far we've got. I won't do much on the CPU board yet. There's some logic chips here, but they're 74HC and they tend to be a little bit more reliable than the CMOS chips. So I'm going to concentrate on this board. Okay, I've started by removing the voice chips from their chip beds, and I've just put them in some conductive foam. And that's just because they're quite expensive, and chances are they're not all dead. Most of them are probably okay, but to avoid killing them by accident, I've taken them out. It's just a good idea. So I've started removing the chips already. So I've done one here. This is a double-sided circuit board, so there's tracks on both sides. And that makes it difficult to remove chips because not only do you have to heat this side, you have to heat all the way through the hole, which is plated, and then to the other side of the hole, and then on the other side you've got a big chip that's acting as a heat sink. So you've got to heat both sides of the board and all of the pins to get it out. It makes it a lot more difficult than when you're only heating one side. Single-sided boards are a lot easier to remove large ICs. So we've got a bit of a problem here. There's a couple of different ways you can do it. You can heat one row at a time, so add a lot of solder, add one row, and very gently pull from the other side, one side at a time, but that takes a really long time. It is quite difficult to get enough heat on this side of the board. The other way to do it is to use pliers and cut all the legs off individually first. So go through and cut each leg, then pull the chip off, and then heat one leg at a time with the soldering iron and pull one leg out at a time. And that allows you to get a little bit more heat into the leg because the chip is no longer acting as the heat sink. So that's probably the best strategy for this board. But whatever you do, make sure that when you're finished, you've got a hole that goes all the way through the board before you put the new chip bed in. So after you get the chip out, you're going to need to use a solder sucker or some soldering braid. And at this point I usually add solder to each hole and then put the braid on and try and suck it out. And if I'm unsuccessful, then I just add solder to the hole again, cut the braid off, start again. If you use the very tip of the braid, you can get more heat in and suck more solder out. It takes a lot of time, you've got to be patient. But yeah, there's no other way to do it. If you rush, you'll pull tracks off and it'll start to become a bit of a disaster. So you just got to take your time. There you go. So however you choose to do this doesn't really matter, as long as you get it all out. I find the braids pretty easy. So I finished the first pass using the desoldering braid and I've managed to get all of one side. The other side there's 4 holes that still have solder in it. So I'll add solder to them now and then use the soldering braid again. If you don't add solder, you find you can't suck up the solder that's left in the middle. So you need to add some solder to help with the capillary effect with drawing out the solder. And that one's done. Okay, all the IC sockets, or the chip beds, are now in the circuit board. And I've put in the 4 4051s and the 3 4066s. I've only put one of the voice chips back in because I'm going to test them one at a time. I've got the other 5 here. I just chose one randomly at the start, but I'll write on them with a silver texture or something so I can keep track of which one's which. And then I'll cycle through each of those one at a time, testing them to see if they work. But first, we have our first calibration to do, which is the power supply. So before I plug in the circuit boards, I thought I would calibrate it. So this calibration is quite simple. All we're doing is calibrating the negative side of the plus minus 6 volt supply. So our reference is the positive side. So if we've got pin 7 on this P4 connector, and we put our positive on pin 3, which is the positive output of the 6 volt supply, and we measure what that is, and then we change to pin 4, which is a negative, and we match the negative to the positive with this pot. So let's do that now. And we're getting 5.8 volts for the positive part of that supply, which is pin 3. So if I change my probe onto pin 4, we're now looking at the negative, which is negative 5.8. It is spot on. That's awesome. So all I need to do now is plug in these cables and we can start testing the voice chips. Okay, here we go. I'm so excited. Turn it on. We've got lights. Okay, so I'm pretty sure that chip is in the voice 1 position, which is on the left hand side. So whatever key I choose, hopefully the first voice triggers. Yes, sounds like it. Let's just reset this cutoff. Awesome. Okay, so what I might do to make it easier to do the test while I'm holding the phone is put the arpeggiator on. Where are we here? Hold. Do octave. Cool. Alright, so it looks like that voice works. Okay, so voice number 1 comes out. And voice number 2 is in. And it works, yes! Chip 3. Yes! 4. 5. So they all work. That's awesome. So I'll put them all in now. Okay, so we've got all 6 voices and they're completely out of tune. Yeah, that's pretty bad. In fact, around about here, oh here, look, that's the same note on 2 keys. But if you have a look at the top of the keyboard, we're actually in tune. So we're in tune at the top half of the keyboard and we're out of tune in the bottom half of the keyboard. Now the keyboard matrix isn't really that difficult, it's just a bunch of diodes. So I know that if we're triggering keys that the keyboard matrix is fine. And it's likely that because we've got the top of the keys in tune, the CPU is giving out the right control voltages. But something goes wrong when the control voltages get lower. So if you watch here, if I change the octave to a higher one, say 4. Oh, the switch is a bit bad. Try and get to 4. Yep, got it. So if we have a look, that's in tune. And it's still in tune. And remember, before these keys were out of tune, but now they're in tune. So it's nothing to do with the keys, it's to do with the control voltages. See, now we're out. That's pretty bad. So what I think is happening is that on either one or all of the chips, the voice chips, they either can't go to a low enough control voltage. So either the auto-tune has had to go to quite low already to get them in tune, that there's really no range left for them to go any lower, and they start to go out when you go lower. Or there's actually something wrong with that sample and hold circuit, and at lower voltages we're leaking or something's going wrong. So I don't know, I'm going to have to test. Okay, the voice board is out again, and we're going to have to understand how it works to fix this tuning problem. So initially when we replaced these CMOS chips, it was pretty much a good guess, because we know that CMOS chips tend to fail, and if we replace them we would fix a whole lot of problems, which we did. The board started off with only one voice working, and by replacing these CMOS chips we got the other 5 working. We've got all 6 voices working now, except that we've just got tuning problems. So the reason why replacing those chips worked is more to do with the 4051s than the 4066s. So these 3 at the top, they're just switches, and they just switch between the sampler input and the noise input, and they feed that to the external input of this CEM. So all they're doing is selecting whether the sampler or the noise is off or on. But these 4051s have a really important role. To explain that, we've got to explain a little bit how the control voltages work in this synth. So with polysynths, there's so many sliders and switches and voices to route those voltages to, that we would need a processor with hundreds and hundreds of pins on it if we wanted to do all of that with 1 pin per function. And we can't do that because the chips just, particularly in the mid-1980s, just didn't have enough pins. So what we need to do is take all those pins down to a smaller number, or something manageable. So the way we do that is we take one single control voltage only from the processor, and we switch that to a whole lot of different places. So effectively we've got one wire coming from the CPU, and we switch it to the VCO control voltage, the VCF, the VCA, all the other control voltages we need on each voice. So we switch it to a whole lot of different places, one at a time, on every voice, and that's what the 4051s do. So there'll be one control voltage input and a whole lot of addressing instructions for these chips, and these chips will switch it to all the different places that it's needed, and the processor will control the different voltages as it does that to set the different values for each voice. And that's how we get away with using lots and lots of pins and just use 1 pin only. Now that's a brilliant idea, but there's one really obvious problem, and that's when we move the voltage from one control voltage input on the chip to another one, it disappears from where it was previously, because we're literally moving it from one input to another. Now the problem is that these chips are analog chips, and they need that voltage on all the time. So if we just used 4051s to switch that control voltage around, it would only be momentarily applied to any of these chips, and as soon as it's removed and moved to a different input, the one that it was on, that information would be lost, so nothing would work. So we need another type of circuit to help us do that. That's called a sample and hold circuit. So in this area of the board here, you see a whole lot of capacitors, and these single inline package chips are op-amps. And these, combined with the 4051s, create sample and hold circuits. So when the 4051s open to let that control voltage in, it fills one of these capacitors, and on the outlet to the capacitor there's the op-amp. So effectively what you're doing is, on one side of the capacitor you've got a brick wall, which is the op-amp, and the other side you've got a switch. So the switch opens, lets the voltage in, fills the capacitor, hits the brick wall, stops. Then the 4051 closes, and that voltage is now trapped in here and held, and it can't get out until the switch opens again. And when the voltage is in that capacitor and held, the op-amp can read that voltage, and then it mimics that voltage and outputs the same voltage to wherever it needs to go on the chip. So you have one op-amp for every single control voltage input that we need in these voices. And the op-amp's what holds that voltage constant on these chips and makes everything work. So when we're troubleshooting control voltage problems, we need to know, is the switch opening correctly, which we know they are now because we replaced them. Is the voltage held in its original value in the capacitor, which we don't know? Is the op-amp able to output that same voltage? And is the chip in the right, is the input of the chip in the right range to accept that control voltage? So there's a lot of areas that we need to check. So checking these capacitors is fairly easy. The op-amps, I suspect, still work, but they hardly ever fail. And the only other question is the control voltage that we're trying to use to set the pitch, is it in the right range? Okay, this is the schematic for the CEM3394 synth on a chip. You can see here, pin 2, we've got our VCO frequency CV. So this is the CV from the keyboard plus the offset that the CPU has determined it's needed to get this particular chip in tune. So I think that the natural keyboard CV plus the offset is causing a problem. Now, Curtis provided a way to naturally change the base frequency of this VCO just by inputting some current into pin 1. So this is a current controlled oscillator. So you'll notice this is not a voltage divider, it's just a resistor. So if we put a variable resistor here, we can change the current going into the exponential converter, which will change the base frequency of the VCO. And then hopefully our offsets here can become more normal to get the range we want. So that's the theory. The other thing we will need to do when we're tuning is that we'll need to know which of these chips we're actually tuning. So when we press a key on the keyboard, we need to know which chip is making that sound. We need to know which chip to tune. So to help do that, I've got some diodes here, and I'm going to connect those diodes to the inputs of the VCA for each of these voices. So when we hit a key, the LED lights, and so we know which chip is currently making that sound, so it makes it easier for us to tune. Now I've already done one of these. As you can see here, I have my LED that's connected to the right hand side of R94. So R94, 95, 96, 97, 98 and 99, they're the input, the VCA control voltage input. And you'll notice something really handy as well, which I was surprised when I saw, is that Akai have provided an area on the board where there were components previously used to tune these chips. So there's already an offset resistor and a variable resistor that work together to tune the chip, but when they've assembled the board, they've just bypassed it with this 270k resistor. So you can see it on here, that in the Curtis schematic, they've just put a 270k resistor. There's like a nominal value. Now it looks like that Akai have thought about being able to tune each chip individually, but then guessed, oh, it's probably just going to be too hard, so we'll just shove in the resistor that's in the data sheet and hope for the best. Okay, the LEDs and the trim pots are in, so you can see the LEDs and then the blue trim pots. So if I hit the key now, you can see voice 1's assigned, voice 2, 3, 4, 5, 6. I can play some chords. And you might have noticed something. It's actually in tune. I fixed it. The Autotune works perfectly now. It doesn't stall like before. And the keys sound good. So I'll just do an Autotune. You can see it. You can see it run through its routine during one voice at a time. Look, it's finished already. Wow, that's so quick. Look at that, it's in tune. Well, except for me talking. So the fix wasn't actually the tuning pots. I've left them in to show that you can actually tune each voice. So if we pick a key, let's see this key, C, we're on voice 1. So if I just move this pot now, and I go back to C, voice 1, see we've just moved 2, 3, 4 semitones. So it was an A, and I'll move it back now. We're back to a C. So you can tune by using these pots, but you don't need to. This would be a really cool mod though in Unison, because if you brought these pots out to the front panel, then you could detune the voices and even do a spread over several octaves. That would make a really fat Unison sound. So the fix was actually really close to what I thought it was. I was on the right track. So do you know how I said that it was something to do with the CVs as we got lower? It's like they ran out of range, and then they were all a bit wonky when they got really low. Well, these tuning pots gave me an idea. I was reading the data sheet for the CEM3394, the voice chip. And the data sheet says that the nominal voltage for the negative supply is minus 6.5, and that will give you the ability to feed the VCO minus 4 volt control voltages. But if the negative supply is minus 5 volts, so it's higher than the minus 6.5, so we're more positive, that limits the maximum negative control voltage of the VCO to minus 1.5. So even changing the negative supply rail from minus 6.5 to minus 5 gives you a difference of being able to put into the VCO of minus 4 volts compared to minus 1.5 volts. So if we change this negative supply even a little bit, it affects massively the ability of the VCO to accept negative control voltages. So all I did was make the negative supply more negative, and then that fixed our negative supply, the negative control voltage problem, and it meant that we could go lower and lower and lower on the keys without going out of tune. So the problem was, well, the problem was the AX60 service manual. That was the problem, because it told me to match the negative supply to be the same as what the positive was. So if the positive was 5.8, I made the negative minus 5.8. But the CEM chips are expecting minus 6.5, or else they have trouble with really low frequencies. So once I just grabbed that pot and turned it until it was as negative as it can go, which ended up being minus 6.3, which is pretty close to minus 6.5, what do you know? All the keys worked and the Autotune worked perfectly. So the fault's really the Akai service manual. So that's a really easy fix. So if you've got an AX60 that's not tuning, or the Autotune doesn't work, try making the negative supply more negative. And that puts it in the range of what the CEM chip is designed for. And then you'll be surprised the Autotune might even work. So that's amazing. So it's fixed now. And I can move on to cleaning it up and restoring it. Awesome.